So just miss full screen. Okay. Hi everybody, I'm Luca, and today I'm going to present, surprise, another BMA package in Gretl. And as you can see, this is a joint work with Jack, and the package's name is ParMA, which stands for Parallelized Model Averaging. We will see very soon the why, but just some details. Okay, for some reason, okay. Um, the details, I said. You may wonder, what is the motivation of another BMA package in Gretl? Well, the answer is pretty simple, because we are using a tool for dealing with generalized linear model with BMA. We've seen that the previous three packages deals with linear models, which are probably the most common generalized linear model, but is actually a specific one. So a practitioner may be interested, for example, in binary or count model. And dealing with such kind of model, as we have seen previously, it's particularly complex, and more general framework for BMA is required. What is done in our package is using the reversible jump Markov chain Monte Carlo sampler. And in order to deal with the computational burden, we introduce parallelization using MPI. The package is built upon four main functions: the BMA GLM, which deals with most of the words. We have then a printing function, BMA printout, and two post-estimation, let me say, function that is marginal graph for plotting, for example, the model averaging posterior distribution of some coefficients, and MCMC checks for diagnostic tests on the quality of the chain of the Monte Carlo. But before digging into the details of the package via an example, I would like to spend some words on some technicalities, in particular the reversible jump Markov chain Monte Carlo framework. To clarify this point, I would like to start from the scratch, from the standard Metropolis Astic scheme. In standard Metropolis hastings, we sample a parameter of interest, let us say beta, from a proposal distribution built upon the previous step parameters, and we accept this step with a given probability. The point is that this parameter is, as always, the same dimension across the space. And if we are willing to translate this in the model averaging framework, as we have seen previously, this is done, for example, with the MC-cube framework. We should simply translate our parameter of interest into a binary vector full of zeros or one, which represent variable inclusion, and sample this element, which actually represent the model. But again, this vector of 0 and 1s will always have the same dimension. And the point is that we have two major shortcomings. The first one is that we need some sort of analytical formula for the posteriors, and this is not actually possible for most kinds of generalized linear models, as I said previously. And the second one, we are actually not paying attention, or at least we are not directly paying attention, for example, to the model parameters. For example, the coefficient attached to the regressor of the linear index in the GLM. And to deal with this issue, we use actually the reversible jump Markov chain. That is, we put together models and model parameters and sample this element. Of course, in this new element, let us say theta, we will have the first part, which is nothing but the vector full of 1 or 0, which will have the same dimension across the space. But notice that now the related parameters, let us say beta I, will have different dimension, because, for example, in a restricted model, we will have few parameters, but on the other hand, in a more general specification, we will have lots of these elements. So we are actually, via this scheme, able to sample parameters of different dimensionality. I will not go through the details of these, but if you're interested, maybe we can spend some additional words at the end. What I can say is that, of course, introducing this scheme is quite easy from a computational point of view. And the idea is to tackle this issue via parallelization and the MPI architecture in Gretl. The point is that parallelization is not an easy task when we deal with Markov chain Monte Carlo, because simply we have correlated chains. We have the Markov property. So what we have done in particular is use the so-called vertical parallel chains. That is, we split a single long chain in several smaller ones, which are run in parallel, and with this idea in mind. If convergence to the target distribution is quick and the burn-in time is not so long, well, we then can reproduce the same result of a single long chain, but with a massive time gain. And moreover, we encourage a better exploration of the space. Again, in order to do so, however, we should ascertain that the convergence, the quality of the chains, and that convergence is achieved. This is done with several tools. In particular, we provide the Bluch-Engelmann statistics, both univariate and multivariate one, which are provided by default by the main function. But in the MCMC checks function, we have also additional tests, such as the Geweke one, the Heidelberg and Welch, effective sample size, and some convergence plot too. So just to have a real idea, we will see the example. And in particular, I've chosen a Poisson model regression coming from an example by Cameraman Trivedi on doctor visits. The dependent variable is simple, the number of doctor visits, and we have this bunch of regressors: sex, age square, income, dummy variables for the kind of health insurance, number of illness, number of reduced activity days, and so on. And just to have a grasp, this is the standard estimation result from a Poisson model. We can see immediately from the last two columns the significance of the variables. Just to have an idea, we can see, for example, that the variable illness and ACT days are extremely important. The same is not so true, for example, for the age or age square, for example. But probably what is most interesting is the BMA counterpart, that is the output of our function. And in particular, this is actually the visual output of the ParMA function, the BMA GLM. I will not go through the full detail of the setup. I can just say that I'm using the default setup, so a uniform prior for the models, a normal distribution with a Zellner-like type prior for the parameters. I will use 100,000 iteration after a 10% burn-in, and I will use 4 chains, 4 parallel chains. These are the sampling statistics of the parameters. In the first 2 columns, we have the mean and the standard error, which are computed actually with this implicit idea that is, if a variable is not included in the actual specification, its parameter is artificially set to 0. So we have a sort of shrinkage effect. On the other hand, if we are interested on the counterpart, but conditional on inclusion only, just have a look on these 2 columns, C mean and C standard error. We have also the probability, the posterior inclusion probability, just to have an idea on the significance on the variable. And as you can notice, for example, ACT days and illnesses are again extremely important. The same, for example, is not true for age square and so on. And we have also some diagnostics. We have the univariate Brooks-Engelmann statistics and the multivariate one. And the idea is that the closer this value is to 1, the better is the chain has achieved convergence. And in general, the threshold considered acceptable in empirical practice is that this value should be below 1.10. And as you can notice, in this case, we are, of course, below 1.10. We have also some details about model posterior model probability. And just coming to the other function, this is, for example, the marginal plots of the model averaging posterior distribution of some coefficient. This actually combines an histogram and a kernel density. And we have, for example, free poor, ACT days, income, and so on. But probably what is even more interesting is some diagnostic checks with, for example, some using the graphical tool. And in particular, I've considered again the parameter related to the ACDAIS regressor. And we can see in this panel that we have the time series plot of the drawings of the Markov chain. We can see immediately that the series is stationary and ergodic. We can have a grasp also on the autocorrelation. We can see that at least at the first lags, we have high autocorrelation, but then this decreases smoothly, and also a look on the convergence of the sample mean. Finally, and I will conclude with this last slide, the contribution of parallelization. I've just replicate the same example, but using more iteration, for example, this time 200,000 after again a 10% burn-in. And I will use from 1 to 32 cores, threads. And in the left graph, you can see the plot of the CPU time. You can see immediately how the contribution of the MPI and the parallelization is extremely huge using more cores and reaches a minimum at the 20 core. What is probably a bit, may appear a bit strange is that after the 20 core experiment, we have a sort of deterioration of the performance, but this actually comes from a technical detail. That is, we are switching through, between physical to logical threads. So there is actually a deterioration. On the right, instead, we have just a look on the convergence statistics. And yeah, there is a sort of increasing pattern, but again, in every experiment, we are below the threshold. So this is it. Thank you for your attention. If you have any question, please, these are welcome. Thank you.
Okay, hang on, okay, so I unshare the screen. And so if anybody wants to say something on this presentation, okay, I've got a raised hand by Jacek, and okay, and maybe other people can, chime in if they want. Jacek, please.
Thank you. That's quite odd situation because I have a question to my co-presenter, Luca. The first thing is I'm a very big fan of your package, and just one question: what is the starting point for your model? I mean, initial model in the Monte Carlo integration, because I know you can set up some just dummy variables to set initial model in the Monte Carlo integration, but have you considered any just automated method to ease the process of convergence, for example, in your package?
Well, the starting point is chosen by the user. By default, it's set to the full model, and then through the Markov chain is directed to the target distribution. You may choose different different starting point, even using parallelization. For example, it is quite common to use a different starting point for each parallel chain. You can start from the null model, from the full, or any combination, but actually there is not a target way to choose a particular model to start with.
Okay. Thanks. I see Mark with a raised hand and Alan as well. Mark.
Yes, thank you. Thank you all for very, very interesting presentations. I have just two sort of clarifying questions, really. One is to Marcin and Jacek. I was very interested in seeing your sort of results for the say for the Henry M1 data, where you used both the BMA ADL and the base sort of software, and you got rather similar results, which is interesting. I was just wondering how different are the priors, because in my experience, whenever you have sort of one one method that gives you perhaps a broader range of PIPs than another run, often it has something to do with the prior assumptions that you're using, and I'm not sure whether you can make the priors exactly the same in these two softwares. So maybe you can say something about that.
Would you like to answer straight away, or
it's up to you? It's up to you. I don't mind. All right, and for Luca, I thought it would be nice to have I think you mentioned briefly something about the prior, because you're talking about the GLM, and in the GLM, in contrast, if you want, with the sort of normal linear model, there's perhaps less of an agreement as to which priors people use. I mean, there's a couple of options if you want. So I just wanted to, if you could give a bit more detail about what prior in particular you're using for the results that you're getting.
Yeah, for sure. For models, the standard setup with independent Bernoulli for each probability of the variable. For the model parameters, instead we use a normal distribution, and in particular, the prior mean is up to the user. By default, is set to zeros. Mm-hmm. Instead, for the variance, for the covariance matrix, we have three different options in the package. The first one is a Zellner type, a G type, which is the default one, and you can specify the shrinkage parameter too. Then we have a ridge case too, so an identity matrix with, again, the shrinkage parameters. And finally, this is a sort of customization option that is the user may specify by default the covariance matrix. But this is, of course, is probably the most computationally heavier solution. But actually use a normal prior. A particular case is for the constant, because we don't use a diffuse constant, but we use, again, an independent normal with a very large variance.
All right, thank you very much.
You're welcome, thank you.
Okay, I've got Alan and then Sven.
Okay, a small technical point, but if I caught this correctly in Jacek's presentation, or maybe it was Marcin's, at one point in the GUI, you're asking the user how much RAM do they have. Is that right? So figure out how much space you can explore, I suppose. Just a small side note here, there's something called a bundle or accessor called $system in Gretl, which provides various information.
Sysinfo.
About the sysinfo, yes, you're right, sysinfo, thanks. Which provides various information about the user's system, number of processors, and so on. Right now, it doesn't give the amount of RAM available, but there's no reason it shouldn't. So you should be able to figure that out internally if we put another element into that sysinfo bundle. Might be helpful.
Well, although that should be handled by the operating system, not by the user in principle. Okay. But anyway, okay, I see your point. Is that it? I mean, Alan, are you happy with the?
I'm fine. That was just a
Okay,
brief
thanks.
remark.
So we've got Sven, and then I have a little suggestion for Martin and Jacek. But okay, Sven.
Right. I just wanted to repeat the question I wrote in the chat. So it's not quite clear to me after those presentations. So BMA, the package, has been around for a while, and now ParMA is sort of brand new, or a few months old, I think. So is ParMA now a superset in terms of the functionality? Because, you know, from the outside, it sounds like it does generalized linear models, BMA, linear, I think. And so, yeah, so that's my question. What is the difference in part from?
May I answer?
Go.
The point is that, okay, in ParMA we deal also with the linear model, but the problem is that the reversible jump Markov chain Monte Carlo is not so effective with linear models. So the computational time is very huge. And so, for example, the BMA standard package, which uses analytical solution, is much, much, much better.
Right, so you don't specialize to that case if you always use the
Yeah,
generic algorithm. Okay.
Yeah. Well, yeah, put simply, the price you have to pay for handling the generalized linear model is that you have to use a much more complex scheme for Markov chain Monte Carlo.
No, sure, that's clear. That's clear. No, that's perfectly clear. I was just, I mean, it could have been the case that you sort of you know, use a different, more specialized algorithm in the special case, but apparently
well,
you don't.
Actually, in the paper that Luke and I submitted to the Journal of Statistical Software that illustrates the ParMA package, we also provide an example on how to estimate a linear model. But of course, that's something you can do, but you'd be very unwise to use ParMA to estimate a linear model. I mean, you're much better off using other packages.
Is that final follow-up? Is that in the documentation for the package? That advice?
Luca, is it?
I think yes.
Okay.
But I don't. I'm not
okay,
so
we'll
sure.
check. We'll check. Okay.
Okay. Just okay. Just a final thing I want to say to Martin and Jacek. I would suggest you to re-specify the signature for your functions, because you've got so many parameters and it's really easy to get confused with those. The recent trend in package writing is to use bundles for options. And I think your code would read much more natural if you used bundles for all the options instead of having this huge string of parameters that you have to supply to a function. But that's just a cosmetic suggestion. Of course, it's got nothing to do with the substantial part of the computation.
Maybe one comment. The good things, most of the things are the default variables. Yes. So if you open this window, you just only specify the wide, I mean, dependent variable, or just top three on the list, and other things you can just look and press
if you
OK.
want to change the default for the 15th parameter, you have to be very careful on how many commas you put in your function. Whereas if you use a bundle, things are, I can guarantee they're much easier. I see that I see a raised hand by Mark.
Yes. Am I unmuted? Yes, I think I am. Yeah. So yeah, just one final question, if I may. I understand this is risky of me to raise in a Gretl conference, but some of the software that you've presented sort of overlaps to certainly to a large extent with software that exists in R, for example. Yeah. Now, if you were to sell, and I'm sure that you know what your Gretl software is wonderful and very quick and all that, but what would you think of? Have you compared the results in sort of CPU times and whatnot with our software for the same functionality? And secondly, how would you sell me, your Gretl software as opposed to our software that I'm more familiar with?
Okay, who wants to have a go? Luca, are you going to start? Okay. Luca first, and Martin later. Martin after that.
As regards computational time, I think that Marcin has just provided in his previous paper some benchmark with R, so he let him answer. For what regards the ParMA package, I can say that at the moment, for what we have seen, there are not so similar counterparts in other packages, in other softwares. Yeah, of course, in R, if I'm not wrong, there are a reversible jump Markov chain Monte Carlo package, but it's quite complex to be used because it requires the previous parameter sampling from another packages, for example. And yeah, there is maybe another package of interest, if I'm not wrong, its name is Pakenselam Gamma, sort of stuff like this, which deals with generalized linear model with BMA, but it use a sort of Spakenslab priors, so it's not very the same thing.
There is a package called BAS, which Maurice Clyde has been involved in, and that does GLM as far as I know.
Yeah, but I've not done comparison, but from what I've seen also from the Marcin example, I can see that in some cases the performance is not so good because it uses tons of approximation. If I'm not wrong, it uses maximum likelihood for parameter estimators, and it uses also the Schwarz criterion, if I'm not wrong, at some point.
It may well do.
Of course.
Yes.
Go ahead. Okay. Martin, just a question. How does your package rate in terms of computational speed versus the other packages? Okay. Okay, so
Sorry, but are you comparing against this table from 6 years ago, or are you comparing with the current versions of them? No, I mean, but when you said today and right now, we're much faster and we're ahead of the others.
okay, and how does that compare to Okay, and how does that compare to other packages in the R environment? Okay, so the answer is we don't. Nobody knows at the moment. Okay, thanks.
And maybe one just comments about some unique selling point. This is the only package with the interface, graphical interface. Yes, and you can just ask someone to precede some calculations without any specific knowledge about the programming R and whatever any program.
Yeah, that's also true. Yeah.
No, it is very convincing. Thank you very much for your answers.
All right. Okay, thank you. If nobody else has any other questions, I guess we could have another little break. On the program, I see the next presentation is by Arthur, and that's scheduled for 2 minutes ago. So I would imagine that, okay, it's now 17, so should we say 25? Are we
okay.
Are we okay with this?
Yep.
All right. Okay, so, okay, let's say we start back at 25.
Good. See you in a bit.
Okay.